Okay. So welcome again, and happy New Year, happy 2025. So let me introduce you our speaker today. Her name is Sabrina Casanova. She did an undergraduate studies in Rome, working on general relativity theoretical problems. Then she worked on the part on distribution functions in QCD, quantum chromodynamics, so theoretical particle physics in Germany. And then she started working on gamma ray astronomy with Brenda Dingus in Los Alamos lab. After that, she worked in Heidelberg with a group of Felix Aronian. And since 2013, she's been Institute Professor at the Institute of Nuclear Physics in Krakow, Poland. And today, oh, sorry, I think I'm not sharing your screen now. Sabrina, can you share your screen?
She's muted.
Yeah, and she can also mute. Okay. Okay. The title is Detecting Microquasars with HAWC. So we hit the ground running today talking about cosmic rays.
Okay.
Please, the floor is yours.
Thank you. Thank you very much. Tell me if you can't hear me. And sorry for my voice. I'm also quite ill. So I'm very pleased to discuss the really nice result we got with HAWC, which is American and Mexican, essentially American and Mexican experiment located in Mexico. So, oh, sorry. Okay, this is just to give you an idea. We are a small collaboration. We are really not so many people, and here you see Brenda, and with whom I work in Los Alamos. So this is the outline of my talk. I will very briefly introduce the HAWC Observatory, and then give you an idea why we are so interested in looking for ultra high energy gamma ray from microquasar. I will skip LS5039, which is probably not a microquasar, for the last, if I have still some time. So this is the location of HAWC. HAWC is a water Cherenkov telescope. So I will show you a picture of it in the next slide. It is located close to Puebla. And what is very, very good for us is that we are at a latitude good enough to look close to the galactic center. And it is 4,100 meters that put us closer to the shower maximum. And this is also a good feature. This is a picture of the instrument. There are 300 tanks, big tanks, which collect water, which collect secondary from shower in a bath of water. And these tanks to collect this light, this Cherenkov light, have 4 PMTs facing upward. There are currently, you don't see in this picture, the other outriggers array, but this is, they were included in 2018. So what is very important of this instrument, large instrument, large array instrument? We don't have a great sensitivity like Cherenkov telescope, like HAWC or Veritas or MAGIC. We also don't have a great angular resolution, which these instruments have. But we have 2 aspects which are very good. Number one, we observe a big portion of the sky continuously, instantaneously, and in a day we reach 8 steradian. We have a very large range in energy, going from 100 GeV up to, in reality, we go now up to 300 TeV. We are up all the time. We don't have to point. This instrument is not a pointing instrument. It just collects photons. The angular resolution is quite bad if we consider very low energy photons. We can't really have angular resolution better than 1 degree, but the angular resolution goes up to 0.2, even a bit less at the highest energy. So the technique I already told you, the water Cherenkov collect the particle, and we measure from all these particles, the secondary produced by the photon or the cosmic ray, we measure time and light, and the level in each PMTs inside the tanks, and we reconstruct core. So the first things we reconstruct is core, energy direction, and background rejection. So the big trouble with this kind of detectors is the bad the bad background level that we have. Essentially, there are few photons in an ocean of, I'm exaggerating, but we have to reduce the background. And there was a long work that, in fact, lasted almost 10 years to improve the background rejection. And with PAS5, we really reach a very good background rejection, better angular resolution, in fact, and what is very important for sources like transient, we have a very improved sensitivity at 100 GeV. Sorry. Okay, why we do it? We do it because we are slow. I mean, now we are already going into a new paradigm for cosmic rays. You know, at the beginning, we had this local cosmic ray spectrum that was featureless up to PV, and we believed that the supernova remnant were the major cosmic ray contributors. They provided their energy, the right energy budget, and also diffuse shock acceleration was working very well in supernova shock. Nowadays, there are many challenges. So, first challenges is that we detect in gamma ray astronomy, we detect cutoff in the supernova spectra. So we can't expect supernova to be able to accelerate 100 TeV. We could look maybe in molecular clouds close by, but by now, the situation hasn't changed since 2019. Even including magnetic field amplification, it's difficult to reach PV energy in acceleration in supernova. And we have very high precision measurement in the local cosmic ray spectrum. So we can't say anymore the spectrum is featureless. And we are in gamma ray astronomy, all the gamma ray astronomy environment, the community is really reformulating the cosmic ray paradigm. And we see a lot of classes of pevatrons, and in fact, we see super pevatrons like the Cygnus. And the research focus is no longer to investigate, to look for evidence that supernova remnant are the major cosmic ray contributors. Still, supernova remnant are an actor in this field. But we want the research focus nowadays is really investigate this big long list of classes of cosmic ray sources which are possibly pevantron. The latest discovery of this pevatron, and in fact super pevatron, are microquasars, and this is what. So just to put the subject, the topic in a context, we look for the highest energy accelerator, and for our how can I say, for our our detector is a continuous detector, is an ideal detector to make survey and search of transient. And in this way, we find the new class of pevatron, in fact, super pevatron, the microquasar. And it's not the only one, but this is to put in the context. So, as I said, our main characteristic, the main point of a large array of such as HAWC or LASO is that they look continuously and they make survey maps of the sky. And this is how we found the last microquasar that we discovered. And this was not known before. Then we observed LS 5039, and its nature is not very clear whether it's a microquasar. But previously we had seen in high energy gamma rays SS433. So just this last discovery was really because we were looking at the maps. And okay, let's start with the first microquasar observed by HAWC. So SS433, it's a well-known microquasar, was observed in many times by many instruments in essentially almost all wavelengths. It is well known there is a black hole. It was observed in X-ray, and in X-ray, at the highest energy, it shows a jet. And the accretion is believed to be super Eddington. So it's, by the way, it's the most powerful jet known in the galaxy. And it's baryon loaded, which is good for us because we have an evidence that there are baryon in these jets, and this baryon could be responsible for the photons we observe. When these jets impact on this previously, on this previous supernova, it creates a nebula, okay? And it creates the lobes. So the jet, not the land, the jet impact the nebula and create these lobes, which are seen in X-ray. So this SS433 has been known over a long time. It's a very well-known object in astronomy. So there was always the idea that these powerful jets could have produced very high energy gamma rays. So previously, at previous attempt by EGRA, or also MAGIC and Veritas. Veritas had this for sigma pre-trial, let's say, detection or upper limit. What we did in 2018, we were looking, this work was not done by me, it was done by somebody else in the collaboration. Sorry. They were looking at the emission from this very bright source in gamma rays called 1908. And they look around and they found this very interesting object, nicely coincident with the X-ray lobe I was mentioned to you before. So there was a lot of activity to eliminate this big source, very bright, so bright that is the first source discovered by Milagro. This so very bright. Milagro was the predecessor of HAWC and was not as sensitive as HAWC. But anyway, somehow they eliminate, for instance, they mask out the part of the sky which included also the galactic plane, and they could detect these two lobes with a post-trial significance of around 5 sigma. But it was a combined analysis of the two. What is very interesting is it was already back in those days the high energy reached by this in this detection. So we couldn't make a spectrum with this low significance, and we fixed a data point at 20 TeV. We're already saying that the galactic jets can accelerate particles up to, say, 100 TeV. That was a big result. It was published in Nature in 2018. We could also combining gamma rays and the the plethora of information on X-rays, we could give an idea about the magnetic field in this jet, at least in the part of the jet that produced this gamma, because the jet starts somewhere here. It's absolutely silent up to the point where it reaches the interstellar medium, impact with that, and produce these two lobes. So considering the energy budget, maybe electrons are, no, maybe, for sure electrons are more favored. However, we can't exclude that this object accelerates also protons up to the highest energy. Recently, the same people who published the first paper reanalyze these two lobes with PAS5 with many more days of data, and with increased significance they could detect the two lobes separately, and they could show that the energy the highest energy reach in the lobe spectra was around 100 TeV. So later on, HAWC looked for instance, energy-dependent morphology, so a strong sign of electrons producing this emission. And so, because if you have, of course, if you have energy-dependent morphology, this works very well with the idea that the highest energy electrons are cooled down quicker and earlier. So, yeah. And, this slide comes from another seminar that I gave. Samar, Safi, Arp was speaking after me. But yes, it's in 2022, at the same time with the HAWC detection, this works, very interesting works on X-rays, hard X-rays was published. And the place where we have detected already in 2018 our lobes are the place where the hard X-rays reaches the highest energy, meaning they're really the same electrons probably that make photons, make also the X-rays. So let's come to the paper that was published last year already in October.
Sabrina,
yes.
Sorry for interrupting. So this is the 5 minutes warning.
Okay, I will make it. So this is the detection that we published in October 2024. So V4641 is an object that is not like S433. It's not persistent emission. It's a transient X-ray, a transient that when burst is very powerful. So it was observed the first time in 1999, and X-ray flux reached 12 Crab in 8 hours. it has a black hole, it's well known. There is also a superluminal accretion going on with a good Eddington luminosity, and the jets are superluminal. I mean, the speed of the jet is 9.5 C, the apparent speed of the jet. This is the X-ray jet that was the radio jet that was observed, and this is to give you an idea. So this is a transient. To give you an idea, it's very quiet. When it doesn't do anything, it's very quiet. This is Chandra observation of this same object in a quiescent state. Doesn't do very much. The X-ray observation are obviously focused on X-ray outbursts happening roughly every 2 years. And the quiescent state, nothing. This is instead what we observe, absolutely persistent emission. This is clear. I mean, to find that we can exclude temporal modulation of this source, I mean, temporal variation of the sources, but it looks like persistent emission. This is the location, I can show you, this is the location of B4641, Sagittarius, the X-ray transient, and at a distance of 55 parsec, we detect a lobe. At a distance of 30 parsec, we detect another lobe. This is the map when we look at the emission above 1 TeV, and this is the map when we look at the emission above 100 TeV. And what is very, very interesting of this result, it is that this is a source that lives in the highest energy. So if you look at the significance above, in fact, more than 1 TeV, the significance above 10 TeV is 8.8 sigma, and the significance of this source above 100 TeV is about 5 sigma, which means it's really in photons, it's a source that lives in the highest energy, and it's extremely elongated and extended. The two things are problematic. So on one hand, we have power loss spectra without any sign of a cutoff, up to 220 TeV. And on the other hand, we have a huge source, which makes it difficult to be explained as with a leptonic emission, with inverse Compton. So we look at the quiescence and the bursting time variation in X-rays, and we try to see if we had any signs of modulation in this time intervals. No way. We look for many time variation. It seems that the source at ultra high energy above, in fact, this source really lives above 10 TeV. It seems that it is a persistent source. So when we thought about the origin of this emission, we have problems to explain this emission with electrons. The reason being that electrons of at least 200 TeV at the termination shocks are needed. And to reach this, you have to continuously beating up cooling. So the highest energy electrons are accelerated somehow. Let's say that you reach this speed, shock speed needed. But at some point, you have to transport them in these very extended sources of the order of the two together, 100 parsec. And the cooling time is very short. So either we reduce the magnetic field in the source, or we keep them long. And this is what is said here. So you have to, on one hand, you cool these electrons. On the other hand, you have to let them diffuse in these big sources. And you need to have a very long confinement to do this. And even in this case, you have trouble. With the protons, you have, so electrons suffer of cooling. For protons, the problem is escape. They don't cool enough. And because there is no big target material, at least as long as we know that. So the protons of 1 PV that you need to explain this emission would escape so quickly that they wouldn't make the emission. So we calculate this ratio between the cooling, PP cooling, and diffusion time. And what it comes out that if you want this source to be able, with the Eddington luminosity, to be explained with protons, you need to slow them down. And this is a feature that is observed in many sources. There is a long confinement probably happening around cosmic ray accelerators. So we detected up to 220 TeV. Immediately afterwards, LASO looked for the source and detected 800 TeV, making this source really photon energy close to 1 PV, yes, photon energy, which makes this source a super pevatron, injecting particle up to 10 PV. So, and also has confirmed the detection, the discovery by HAWC. So this, I think I will skip it. So just to let you know, as I said, SS for free is a very intensively studied source. V4641, not at all. We are trying to get more X-rays from this source. Unfortunately, our proposal, one of our proposals was not approved. And we are also working on radio observation to try and better understanding the distribution of gas in the region. Gas is the target for protons to make gammas. And okay, there is also expected neutrino flux. I leave it for you. So at some point in HAWC, we thought, okay, what do we have in HAWC with microquasar in terms of acceleration of cosmic ray inside? Well, on one hand, we realized that the photons emission, the gamma ray emission, seems to be coming from it seems to be persistent. So SS for free has persistent black hole activity. V4641 has intermittent black hole activity. However, the gamma rays are very persistent in both cases. It seems that having very fast jets helps a lot. And it seems also that the accretion is super Eddington in both objects. Considering so this is for what we know in terms of binary system. What we know about the emission of these objects in gamma rays, we have hard spectra, which do not show any cutoff. In fact, with V4641, we have 800 TeV detected with LASO. The morphology of the emission seems to be similar, despite the fact we couldn't, that with HAWC, we couldn't say for sure whether they were lobes or extended sources, but they are very extended objects. This is no question about. And also the location of the acceleration. So when the jets impact somewhere, the interstellar medium seems very similar. I don't have time to show you another slide, but if you look at the map of SS433 and V4641, the emission comes from the same origin in parsec, similar distance from the central binary. So this is what many people now claim. I don't think that it's something that we can't forget. That these are really very interesting objects to have sub-PV or even 10 PV, sub-PV electrons, or even 10 PV protons. And yeah, now this is LASO. Last slide, I think. So LASO extended this. As I said, they observe 800 TeV from V4641, and they observe other binary microquasars. I mean binaries which are microquasar. So it seems that these two objects, SS433 and V4641, are not the only one in this class. So yeah, these are my final slide, but LS5039, I skip it. So we have discovered multi-TeV gamma rays from SS433. The extension of these very extended lobes is the energy range is up to 100 TeV. From V4641, we have discovered from this big region 100 TeV, several hundred TeV gamma rays, and we are really very much busy with multi-wavelength analysis, because this source hasn't been so much studied as SS433. Last but not least, next year we will add to the analysis 6 years of outrigger data. I mean, not next year, this year, starting from now. So maybe we can detect something more at the higher side. And that's it. Sorry if I spoke too long.
No problem. Thank you so much. Let's thank Sabrina again. Okay. Do we have questions from here?
Very nice talk. I always thought V4641 was a black hole low mass X-ray planet, as you said, have B star companion. That's news.
Sorry, I can't hear you.
Okay, I thought that V4641 Sagittarius was a black hole low mass X-ray binary, but you mentioned a B star, which makes it a high mass black hole, high mass. That's news to me. That's just very
Really? This is. I hope we didn't make this mistake because we wrote it in Nature, but I can check this. Okay, let me go back. This is really not my. But I think we got it. Maybe there is also the citation here. So. Yeah, it's 4.6 solar masses. It's not. You think of tens of solar masses or even more. Yeah, they are quite, let's say, yeah, small black hole, but also SS for free. Let me see, I don't remember SS for free. What is the size of? Yes, 8 solar masses. They are not black holes of masses. Thousands, billions of the solar mass. They are galactic objects. I didn't say this, but one of the things that was pointed out to us by the referee is that we are, what you are saying is very emphatic, very important, because we are detecting jets which accelerate particles to very high energy in this relatively, you are right, relatively, let's say, I don't want to say normal, but not so extraordinary objects like extragalactic AGNs. And this is one of the points that makes it's very interesting that we have these jets more often than we thought in the galaxy. And accretion works so well, probably accretion driven, that they reach this very powerful, they have these very powerful jets. But yeah, it's right. They are not big masses. Sorry.
Okay. Any more questions from here? I don't see online questions. We probably should write up because of the incumbent CfA wide. But please, if you have questions, sign up with the on the Google spreadsheet to have a meeting with Sabrina. So let's thank Sabrina again.
Thank you. And sorry
Next
for
week we don't meet because of the AAS, so we'll meet in 2 weeks from now. Thank you. Have a nice AAS meeting.
Thank you.
Grazie.
Ciao, grazie mille. Ciao.
Un po' di domande, ti mando un paio di domande poi dopo,
Ok.
magari finiamo.
Ciao, magari rispondo domani, non oggi.
Un capo,
Ciao,
anche la prossima settimana va bene.
ciao, ciao.
Ciao.